subscribe to our YouTube channel, Joy Learning TV.
Hi everyone on Joy Learning channel with me, Wisdom Agbesinyale. And always you can call me Wizzy One. Yes, acids and bases form part of us. In our homes, cleaning materials are made up of bases. If we talk about soap, it's basic in nature. Talk about toothpaste, basic in nature, and so on and so forth. Then we can talk about acids. Oranges that you take is acidic. Pineapples, bananas, apples, they are all acidic. The vinegar you use to wash your fruits and so on is also an acid. So the acid can be a strong acid. The base can also be a strong base. How do we determine whether it is a strong base or a strong acid? We will talk about its dissociation ability, whether it's going to dissociate completely, that is, releasing all the H plus in solution, or all the OH minus in solution, or it is releasing few H plus ions in solution or few OH minus ions in solution. Then we say that acid is dissociating partially. And of course, if you are dissociating partially, then we can describe you as a weak acid. So when we're talking about the strong acids, then they dissociate completely. Therefore, we can talk about the pH, the pOH of such. But if you dissociate partially and you are a weak acid, then we can talk about the dissociation constant, because you are going to establish an equilibrium between the undissociated weak acid and the few ions in solution. In that case, you are going to establish an equilibrium. Therefore, we'll have to talk about equilibrium constant. So, the equilibrium constant for weak acids and bases, we will use K sub A and then K sub B to describe them. That is the equilibrium constant for weak acid dissociation, Ka, or equilibrium constant for weak base dissociation, K sub B. So that will lead us to partial ionization of weak acids and bases. Let's consider a weak acid in water. Let's say the vinegar in your home, you take a little of it, add water to it. So if that is the case, then you will have an equation as on your screen. So let's have a hypothetical weak acid represented as HA in water. So as I said already, it is establishing equilibrium because of its weak nature. All cannot go like that. All complete, no. It goes slowly. So here we are talking about Bronsted-Lowry acid and base. So there will be protonation and deprotonation. So the water here will accept a proton, that's Bronsted-Lowry base, to form the ozonium ion as the product. And then the acid HA is losing the H plus to form the A minus ion as the conjugate base of acid HA. And then the ozonium ion is the conjugate acid for the base H2 O. So this reaction here is Bronsted-Lowry acid-base reaction. The equilibrium expression there is because the acid is not dissociating completely. It is dissociating partially. So anytime I give you an equation like this, it means that we are dealing with a weak acid. That is equilibrium system. So from here, we can use an ice table. Ice table? Is it the ice block in my home? No, ice table. So this one is a table, not the ice block in your home. So this is how it looks like. It's just simple. So the I there is initial concentration of the weak acid HA. And then the C will be the change in concentration. So that is I there. And then the C change in concentration, that is C. And then the equilibrium concentration, that is E. So it becomes ice. So it's not the ice block in your home. Okay, so when we use the ice table, then we can talk about the parameters. That is initial concentration, change in concentration, and then equilibrium concentration. Why equilibrium concentration? Because the dissociation process of the weak acid is establishing an equilibrium between the undissociated acid and the ions in solution. So we have to use equilibrium constant to represent. So we will need the equilibrium concentration of the ions and the acid. You see how beautiful it is? Yes. So if we represent C as the initial concentration of the acid, of course, weak acid, not just an acid, but weak acid. Since it is dissociating partially, it means that initially there wouldn't be any ion in solution. So we have solely the weak acid in solution. As time elapses, then there will be a change. So initially, we have the initial concentration of the acid, and then we have 0 concentration for the ions in solution. So as time elapses, the weak acid concentration will decline. So the moment the weak acid concentration is declining, it appreciates in the production of the ions in solution. So the change, we are using X as the degree of dissociation. How much value of the initial concentration of the acid is declining? How much? So we are using X to represent. You can use any variable to do that, and you'll be free of whatever. X and Y, they suffer a lot, right, in mathematics. But you can use any variable that you want. You just define that is the value declining from the initial concentration and appreciating equivalently, right? Yes, equivalently. So if there is a change, the initial concentration will decline. That's why, so we have to subtract how much of the value is going into the formation of product, that is the ions. So we subtract from the initial. And then as much as depreciation is taking place in the initial concentration of the weak acid, there will be appreciation in the ions. So minus X there, we have plus X plus X. Now because we are using equilibrium concentrations, that will lead us to the equilibrium constant for the weak acid. We will have to find the equilibrium concentration of the acid and the ions in solution. So in effect, we are going to have C minus X, and then 0 plus X, that gives us X, and then 0 plus X, that gives us X. So in effect, we can write the equilibrium constant for concentration of the weak acid. So K sub A is the equilibrium constant for weak acids ionization at a given temperature. Please, it is an equilibrium, and temperature is affected by temperature. The temperature is the equilibrium constant is affected by temperature. So if temperature changes, the constant will also change. So if we are talking about the equilibrium constant, then it should be stated at a given temperature. In that case, it is constant. Right, so we can have our expression. Now from your equilibrium reactions, that is one of your topics in chemistry, it is the reactant on the product. So if we have more than one more than one product, then we're gonna have the product of the concentration, or the product of the concentrations of the product. Get it to product means multiplying. That is in mathematics. Then product means the resulting chemical species as a result of a chemical reaction. So if I say sodium is reacting with water to produce sodium hydroxide plus hydrogen gas, this is the product of the reaction between sodium metal and water. So the multiplication of the concentrations, that is the product. So the product of the concentrations of the product, that is resulting species, when chemical reaction occurs. On the reactant, so from our initial equation, the products are the ozonium ion and the A minus ion. So we are going to multiply the concentrations of such divided by the concentration of the weak acid. So that's what we have there. But we are representing those things with x, and then C minus x. So we can represent the concentration of the H plus to be x, and then concentration of A minus to be x, and then of course the concentration of the weak acid to be C minus x. So wherever we see such, we do substitution. This is mathematics. So we do the substitution there. So multiplying, we can have x squared on C minus x. So that will be our new expression as that. But we can make an assumption that because the degree of dissociation is so negligible, we can equate the C minus x to C. That is, if the value of x is less than 5% of C, then this assumption will hold. So if we are doing the calculation, we must assume that the degree of dissociation of the weak acid is negligible. So therefore, the initial concentration will be equal to C. So doing, we can make x squared the subject. So making x squared the subject, I can have X equal to root of CK. And don't forget, this X there is the same as the concentration of hydrogen ions in solution. So this expression, I can also say the concentration of hydrogen ions in solution equal to root of the initial concentration times the dissociation constant for the weak acid. And that's we have here. But anytime we talk about the concentration of hydrogen ions in solution, then we can talk about pH. And pH is the negative log of the hydrogen ion concentration in solution. So I can write the concentration of H plus as the initial concentration times the dissociation constant for the weak acid power half. So with that, I can take negative log of both sides because I'm looking for a pH. So if we do that and we expand, we will have negative log concentration of H plus ions in solution equal to negative half of log of the initial concentration of the weak acid minus half of log of the dissociation constant for the weak acid. Don't forget, keep this. But this negative log concentration of H plus ions is the pH. So that will give me this one here. I can write it as plus half negative log Ka. You see. So this negative log Ka is pKa. Just as we said that negative log concentration of H plus ions equal to pH, therefore the P there is the potential of hydrogen ions in solution. So the P here is the potential of the dissociation constant for the weak acid. So in effect, I can have negative half log initial concentration plus half potential of the acid dissociation constant for weak acid. So rearranging, I can have my pH equal to half pKa minus half log of the initial concentration of the acid. So keep that as well. And that we have there. So in calculations, you can decide to use that or use this, depending on the question that you have been given. Let's make some statements. So the strength of an acid is expressed as 8 Ka or pKa. So it means that if you know the values of Ka or you know the values of pKa, you can determine the strength of an acid. So if examination can have it that you are given an acid, it could be variables with the dissociation constant or pKa. Then they will ask you to arrange this in order of increasing strength of the acid. So with the values, you should be able to do that. So if Ka is high, then it means that the acid will also be strong. So Ka is directly proportional to concentration of H plus. So if I have high Ka, it means that I'll produce more H plus ions in solution. That is the meaning of it. And of course, it is inversely proportional to the pH. And then inversely proportional to the pKa of the weak acid. So from here, we can express that pH is directly proportional to pKa. So please, these are the concepts that you should keep, because out of them, a question will be given to you. Of course, you should be able to handle it when you see it as it is. So Ka, don't forget, is experimentally determined. It means that you cannot just look at it in any way and say it's so and so. No. Because they are experimentally determined, they are constants. So each weak acid has its own constant. For example, the one for vinegar, as you have it at home, is 1.8 times 10 power negative 5. So it's constant. Anytime you need it in calculations, it will be given to you to work with. Is that okay? So, right, so generally when Ka is 10 or higher, the acid is completely dissociated. That is 100% dissociation and can be described as a strong acid. So please take note. It's not just a statement, but it is very, very important. So Ka is directly proportional to the strength of acid. So higher Ka, stronger acid, meaning higher H plus ions. You see, so this is the summary of everything. If you take it, it will help you in all directions. Talking about strength of an acid, please take note, the strength of an acid is different from a concentrated acid. Weak acid can be concentrated. Strong acid can be concentrated. Strong acid can be dilute. Weak acid can be dilute. When we're talking about the strength of an acid, we are talking about dissociation ability of the acid. If it dissociates completely in solution, we say it is a strong acid. If it dissociates partially in solution, we say it is a weak acid. So take note, get the difference. Whoa. The next important statement we want to make is that if we have polyprotic acids, that is, acids that can produce more than a mole of H plus ions in solution, we describe it as polyprotic acids. So for example, if I have H2SO4, the H2SO4 can produce 2 moles of H plus ions in solution. So it becomes polyprotic. Specifically, because it is producing 2 moles of H plus ions in solution, we can describe it as a dibasic acid because it produces 2 moles. If it can produce 3 moles, then we say tribasic, and it is also polyprotic. So as it is dissociating, it is dissociating step by step. So if I have H2SO4 in water, I'm going to produce HSO4 minus plus H3O plus. You see, so that is Ka1. And then this one is amphiprotic. Amphibian, live on land, live in water. So 2 ways of life. This is amphiprotic because it can accept a proton or donate a proton. So you take note of that. So if that one also dissociates in water, this one is weaker than this. So I'm going to use the equilibrium sign. So I'll have H3O plus plus SO4 2 minus. You see, so here it is, this species here is donating. So it is an acid, that is Ka2. So this Ka2 will be less than the Ka1. So if we know the values, you see that the Ka2 will have a value less than Ka1. Let's look at it, oxalic acid. So oxalic acid is a basic acid. It means that it can produce 2 moles of H plus ions in solution. So the first one has a value of 5.6 times 10 power negative 2, and then the other one has a value 1.5 times 10 power negative 4. It means that this acid here is weaker than this, because we say Ka is directly proportional to H plus ions concentration. You see, so these values are constant that you'll be given most of the times when they are needed in a given calculation. Right, so what have we been talking about? We are talking about dissociation of weak acid. And we said that when we are talking about dissociation of weak acid, it produces few ions in solution. Therefore, when you want to write it as a chemical language, you need to use the equilibrium sign. So if that is the case, then we can find a pH, because equilibrium has been established. So we can write the equilibrium constant for concentration of the acid and the ions in solution. Through that, we can find the concentrations of the ions in solution, we can find the concentration of the acid, and so on. And of course, since the acid is producing H plus ions in solution, then we can talk about the pH of the solution. You see. So let's say, for example, I want to write the equilibrium constant Ka, as we have already learned, for this particular first stage dissociation of oxalic acid. So I can just have Ka equal to, don't forget, the product of the product concentration divided by the concentration of the reactant. So I'm going to have concentration C2H04 minus times ozonium ion concentration, all on the concentration of C2H2O4. You see. So with this, if I know the values, the concentration of the acid, concentration of the ozonium ions, and then that of the oxalate ion, I should be able to calculate the Kc. Or if I know the Kc and I know 2 of these, then I should be able to calculate the other concentration. So there are 4 variables. They will give you 3 and you calculate for the 4th one. Take note of that. If I want to write for this, then I can easily say that I have K equal to concentration C2O4 to minus that of H3O plus, all on C2H04 minus. You see, I can write. Don't forget, earlier on, I told you that this HSO4 minus is amphiprotic. It means that I can donate, that's acting as an acid, Bronsted-Lowry acid, or it can accept, that is acting as Bronsted-Lowry base. So this one here is donating the H plus ion. So that is Bronsted-Lowry acid, and then the water. It can equally act as Bronsted-Lowry base, thereby accepting a proton from water. So this same thing, I can also write it as C2 HO4 minus plus H2O, equilibriumly producing OH minus plus C2H2O4. You see, so that is acting, is releasing OH minus ions in solution. So if it is question, the question will tell you as to what to do. We can say write the dissociation equation of C2H04 ions behaving as a base in water. So if it is behaving as a base in water, then you have this. In that case, we will talk about Kb, that is dissociation constant for weak base. That is our next thing to do. So if I have a base in water, the base will be protonated, or the base will accept a proton, releasing OH minus ions in solution. That means that when the OH minus ions are in solution, the solution will behave as a base. And of course, you know the effect of the solution on indicators. So since it is a weak base, then it will accept a proton. So this one here is acting as Bronsted-Lowry base, and then the water there is acting as Bronsted-Lowry acid to give us this. So here too, we can find the weak base dissociation constant. So I can have K sub B equal to, don't forget, the product of the concentration of the product divided by the concentration of the weak acid. So I'll have that. All on concentration of V. Now, water here is a pure liquid. That is why it must not be involved in the Kb or Ka expression. So, as I said already, in the case of the Ka, we can also do calculations based on this if we know the necessary values. So we can also use the ice table for the weak base as represented on your screen. So here too, you realize that what are we changing? We are only changing the weak acid to a weak base. All other representations remain the same. So Kb is the equilibrium constant for the weak acid ionization in solution. So if they say, what is Kb? Define Kb. Or what is meant by Kb? It is the weak base dissociation constant. Okay, so as we have an idea already from the weak acid expressions, it is the same thing. So you write that represented with X, and then you do the necessary computation. So I can have Kb equal to X squared on C minus X. Don't forget, C is the initial concentration of the weak base. So the moment I see K sub B, I'm expressing the weak base dissociation constant. So as usual, if the value of X is less than 5% of the initial concentration for the weak base, then we can assume that the concentration minus X equal to the concentration C for the base. So therefore, I can write Kb equal to X squared on C. So I can have X squared equal to CKb, and then X equal to root of CKb. So don't forget this. This time, this X here equal to OH minus because the base is producing OH minus ions in solution. Is that okay? Yes, so it's as simple. So they are here, you follow as we did for the weak acid. So in this case, I can talk about, since I'm dealing with Kb, then OH minus ions is in solution. Therefore, I should talk about POH. That is the negative log of the concentration of OH minus ions in solution. So it's the same format that we are applying, right? That way, take negative log and then do your expression as we did already, and that gives us the final answer there. So it's very, very simple. Do not waste your time learning the two together. No. The one you like most, learn that one. And then when you go for an exam, when the question is asked on the other one, you just convert what you know to what you don't know to answer that question. So for example, if I want to quote the pH equation for weak acid, all I need to do is to replace the POH or remove the OH from there. Remove this OH and bring H there. Equal to, it is half log C, negative. The C there is the initial concentration. And then we have half pKb. Remove the B from there and have pKa minus half log C. So the only thing you are changing, let OH go to H and then let Kb go to Ka. The equation remains the same. If you like the pH 1, that is what you know. And the question is on the POH. Oh, very simple. Just remove the H there and put OH there. Remove the sub A there and put sub B and put B there. And that gives you the equation for the POH. Is that okay? But some might say, this equation, I can't keep it. It's not a problem. Very, very simple. You can do without the equation. From the ice table, we had our Kb be x squared on C. That is if the value of x is less than 5%. The assumption or the dissociation is very, very negligible. So from here, I can have x squared equal to Ck sub B. So C there is the initial concentration, and then K sub B is the dissociation constant for the weak base. So if I know this, I know that, I can find x squared value. Then you find x to be root of Ckb. So do your substitution. So when you do your substitution, this x there equal to OH minus ion concentration. So from there, I can quote POH equal to negative log of the OH minus ion concentration. Then you find the POH. Is that okay? So don't worry if you can't remember the working formula as we have it, you have no problem. It's very, very simple. You can work out without memorizing the whole information. So you can do it step by step to get it. Please don't quote a wrong one. When you quote a wrong one, it will go against you in examination, because the question will have to do with substitution and evaluation. So 2 marks, substitution 1, evaluation 1. So if you quote the wrong formula, it will give you wrong answer. So you are losing the 2 marks in a given examination. Right. So we have been looking at Ka, that is acid dissociation constant for weak acid, and then Kb, that is the base dissociation constant for the weak base, or dissociation constant for a weak base, and how they are related to one another, and pH and pOH. Let me leave this with you. We talked about Ka, then we talk about Kb. How are they related? Let's take this example to illustrate. So this is an acid in water to produce that. This C2H04 minus here is the conjugate base for that acid. And then this C2O42 minus is the conjugate base for this acid. So it means I can write the Ka for that reaction. So writing Ka for that reaction, I will have Ka equal to C2H04 minus concentration times H3O plus concentration, or divided by concentration of C2H2O4. You see. Then write this one also. So here is also behaving. So this one is the base, conjugate base for this acid. And I told you that this one here can behave as a base or as an acid. The equation here is behaving as an acid. Let me write the equation as it behaves like a base. So I'm going to have C2H04 minus plus water equilibriumly producing C2H2O4 plus OH minus. So I can write Kb for this. So if I write Kb, I'm going to have concentration of C2, H2, O4 times OH minus concentration, all on C2, HO4 minus concentration. You get? Now let's multiply. Let me say this one is equation 1, equation 2. So let's multiply equation 1 and equation 2. So I'll have Ka times K sub B equal to concentration of C2H2O4 times H3O plus on so that is the product for Ka on C2H2O4 concentration times, so the Kb we will have C2H2O4 times OH minus concentration, all on that. So C2H2O4 concentration times OH minus ion concentration on C2H04 minus ion concentration. Now, what can we do? There are like terms that we have to cancel out. This one here can cancel out that. So let me delete those ones so that we can see it clearly. And this one here can also take away that. So let me clean that. Right, what are we left with? We are left with the H3O plus concentration times OH minus ion concentration, and that is Ka times Kb. You see. Now, if you remember, when water undergoes autolysis, the products of the H plus ions and the OH minus ions gives a value of 10 power negative 14 at 25 degrees Celsius. That is Kw, the ionic product for water. So I can also say that Ka times Kb equal to Kw. And of course, Ka times Kb equal to 10 power negative 14. So if I know Ka, I should be able to use this expression to calculate for Kb. If I know the value of Kb, I should use this expression to find the value for Ka. Take note in calculations. So, for example, if This is the value of Ka for the second dissociation. If I know this and I write this equation C2H4 minus behaving as a base, then in here I should be able to find the value of Kb using the value I have here and the expression we have just produced. So with that, then I'll be able to calculate whatever I'm supposed to calculate in the Kb expression. I hope that is done. So keep it for yourself. That's what I want to leave with you. That is the reaction of weak acid and that of its conjugate base. Take note. Polyprotic acids. The conjugate bases are amphiprotic. They can behave as an acid and they can behave as a base depending on what you have been told. So take note of it so that you are not taken by surprise. Okay, so now that we have the concept, let's see how we can apply. So let's look at examination style questions. Question number 1, what is the pH of 0.100 mole per dm cubed ethanoic acid if its Ka equal to 1.8 times 10 power negative 5 mole per dm cubed? So please don't memorize these values, because in this calculation you can be given a hypothetical Ka. Then you are surprised, but the ethanoic acid Ka that I know is 1.8 times 10 power negative 5. So why is this one 1.7? No, use whatever you have been given when you are solving questions. So here the Ka is 1.7 times 10 power negative 5. So you use that. What do we know? The initial concentration has been given to us. Ka has been given to us. And what are we looking for? We are looking for pH. If you cannot quote the formula, please don't worry yourself. It's simple. So if the value of the degree of dissociation, as we use X to represent, is less than 5% of it, of C, then we can say that the C minus X is approximately equal to C. So our concentration will be C. And then Ka is given. So you agree with me that from the ice table, I can have concentration of H plus equal to roots of C Ka. That's all. So put in the values, roots 0.100 times 1.7 times 10 power negative 5. So that will give us root 0.1 times 1.7 exponent neg 5. So that will give me 1.30 times 10 power negative 3 mole per dm cubed. So I can have my pH is equal to negative log of concentration of H plus. That gives me negative log of 1.30 times 10 power negative 3. That will give me, so negative log answer will give me 2.88 as the pH of this given solution. So if you work and you have 2.9, no problem. Take note of that. Okay, so if we should find this value and it is less than 5% of C, then it means that the assumption we have made here is valid. But if not, then the assumption is not valid. So let's see. So we have found the concentration of the ozonium ion, the H plus ions or ozonium ion is the same, which is equal to X. So it means that X equal to 1.30 times 10 power negative 3. So we can find the percentage X. So percentage X equal to 1.30 times 10 power negative 3 on the initial concentration times 100%. So let's see. We are testing a hypothesis. So let's see. 1.3 exponent neg 3 divided by 0.1 times 100. You see, so percentage value for X is 1.3%, which is less than 5%. So it means that our assumption is valid. Is that okay? So in examinations, please, you solve it as you are given. You are calculating for pH. So use your assumption and then do the pH. Is that okay? Right. So the solutions are there. Question number 2. The pH of 0.01 mole per dm keep methanoic acid if this is this. Determine the Ka of the. So the first one, we're giving Ka, we have to calculate the pH. Here we have been giving pH, we have to calculate the Ka. So don't worry about anything. You know that the H plus ion concentration equal to root of the initial concentration times Ka. So what do I need to find Ka? I need the concentration of H plus. And concentration of H plus is related to pH as pH equal to negative log concentration of H plus. So I will have 3.4 equal to negative log concentration of H plus. So I can have H plus concentration to be 10 power negative 3.4. And that gives me so inverse of log 3.4. That gives me 3.98 times 10 power negative 4. So this is the hydrogen ion concentration. So with that, I can do my substitution and find Ka. So here, I will have my 3.98 times 10 power negative 4 equal to root of C. C is 0.01 Ka. We are looking for that one. So make Ka the subject. So I'm going to have 3.98 times 10 power negative 4 squared. on 0.01 equal to Ka. So find the square of that, divide by 0.01, and that gives me Ka to be equal to 1.58 times 10 power negative 5. You see, so there are various ways that questions can come from here. You have the concept right now, so please look for questions and solve them. As always said, practice makes man perfect. So keep on practicing on Joy Learning channel. As always, I am Wisdom Agbesinyale, and you can call me Wizzy One as we enjoy chemistry together on Joy Learning channel. Joy Learning channel, keep learning. Bye-bye.
Subscribe to our YouTube channel, Joy Learning TV.